Okay. And so our lecture today is going to focus on where we left off last time, talking about this cell potential, which we could calculate from our constants page, from the values that we got on our constants page. Remember, by cell, we're just referring to this particular type of battery that we've been studying. It's kind of the simplest battery, and today we'll look at some real batteries and see how they differ ever so slightly, but have the same sort of basic setup, okay? But again, a big part of this chapter was being able to look at a battery, look at the oxidation reaction on the anode and the reduction reaction on the cathode, and then look up those particular reactions on our table in order to calculate the potential of that battery, okay? And so one of the things that we left off with was saying this idea, well, that if the potential is greater than 0, then that means that that battery would be spontaneous, meaning your battery works the way that you expect it to. Congratulations. All right. And so now we're going to talk about how that concept relates to something that we've discussed prior to with regard to spontaneity, and that is this idea of delta G, right? So let's just hone in on this real quick and say if our E cell is greater than 0, that means it's spontaneous. So then what does that imply for the value of the delta G naught? Okay, so let's do as our first I clicker. We'll make it a multiple choice. All right, so is delta G going to be A, greater than 0, or B, less than 0? If our E cell, our standard potential of our battery, is greater than 0. All right, so I'll give you guys a minute to lock that in. All right, cool. So remember, we talked a lot about this with regard to thermodynamics. If a reaction is spontaneous, that necessarily means that delta G is less than 0. Okay, so we don't really know the relationship between the potential and delta G yet, but we do know if we can, if we have the sign of our E potential as greater than 0, that must mean that our delta G naught is less than 0, because both of those are conditions for the reaction to be spontaneous. All right. So now we're going to talk exactly about this relationship between delta G and the standard potential. All right. So if we remember from our units, we said that the standard potential was measured in something called volts, right? And we defined a volt as a joule per coulomb. Okay, so joule is our units for energy. And specifically in this context, we can kind of interpret it to be the amount of work that could be performed by that battery, the maximum amount of work. Okay, and the reason we can interpret it by that is because that's what a battery is doing, is moving charges over a certain distance, right? So it's performing work on that charge. Okay, and so we're going to use Q for the charge of those electrons. All right. And so then if we rearrange this here, we would get that our E naught of our cell times Q is equal to the maximum amount of work that this battery could perform. Okay, And if we remember back to thermodynamics, that is the definition of what would actually be negative delta G naught. And this is where the signs are just such a pain in the butt for thermodynamics. It's a little bit above the scope of this class, but it really depends on how your textbook defines work as it's being performed on the system, by the system on the surroundings, or vice versa. So consistent with our textbook, work would be a negative delta G. Okay, and then one more thing that we're going to introduce here is this concept of Faraday's constant. Which is equal to the charge of 1 mole of electrons in coulombs. Okay, so that means my charge Q, what I can do is plug in N and F. Okay, so let's just real quick. N is the number of moles of electrons, let's say transferred. In a reaction. And F is that Faraday's constant. So the two of those multiplied together would give you the total charge of that battery. So if we take that E naught cell, we see that this is equal to negative delta G naught. And the convention is to move the negative sign over here. All right, so now we have this relationship between our battery and the free energy of our system. Okay, so let's just take a second and calculate it for that battery that we were just looking at previously. So real quick, also, you got to know the value of F, that would help. So Faraday's constant is 9.6485 coulombs in 1 mole of electrons. Okay, so given these here, we can go take a look at our previous battery and then plug everything in and figure out what the actual free energy of that battery would be. So let's just take, what's the easiest thing to do? Okay, so if we look back here, there's two important bits of information that we need from this reaction. And just to be clear, this is this very first simple battery that we discovered, where we were oxidizing zinc at our anode and reducing copper at our cathode. Importantly, this reaction, when I got my balanced chemical equation, is going to result in the transfer of 2 electrons. Okay, and the standard potential that we calculated for this battery would be that 110 volts, 1.10 volts. All right, so looking at this equation here, we had our E naught cell was this 1.10 volts. And for this particular reaction, there were 2 electrons being transferred. So now plugging everything in, including that value of Faraday's constant, everybody take a second and tell me what the free energy of this particular battery would be. Oh, and we'll do it as a short answer here. Okay. All right, and pay careful attention to your units. All right, so if we're going to be good, we're going to plug in. I'm going to do it with my units here so we can see explicitly how I'm getting this. That N stands for 2 moles of electrons times that Faraday's constant, which is the number of the charge, right? Remember, that's what we're measuring in coulombs, the charge of 1 mole of electrons. And then we have that 1.10 volts, but remember what's a volt? It's a joule per coulomb. So multiplying all that together, I get negative 212.6 something. Where is that? 212.267. But if I look at my units here, my units are in moles of electrons cancel out, coulombs cancel out. So I'm left with joules. And that sort of explains why we get such a gigantic number, because remember, the convention for free energy is to report in kilojoules. So I would then take that value, divide it by 1,000, and I would get my 212.267 kilojoules. Large free energy change for that particular reaction. All right, so now we've sort of explored this relationship that we see between our E naught that we learned how to calculate from our constants page, as well as the actual, free energy of that particular cell, right? So let's then remind ourselves of other relationships that we had learned in our thermodynamics chapter. Specifically, the relationship between delta G and the equilibrium constant, K. Okay. So if we then take our delta G value, remember, R is going to be 8.314, but that's joules. So we're going to divide that by 1,000. All right. And then what is my temperature? How the heck am I supposed to get my temperature? Does anybody know? We can use the chat here. How would we get my temperature for this particular reaction? What does this thing mean? Awesome. All right. So because we're still talking, and we will sort of graduate this concept to include non-standard conditions here in a moment. But at this point, everything that we've been talking about is that fairly restrictive set of conditions where we're still under quote unquote standard conditions, right? So because of that, my temperature is 298 K. My concentration of any solution is 1 molar. And my pressure of any gas is at 1 atm. Those are the only conditions that we've kind of been able to quantify at this point, right? So how do I know what my temperature is? Well, by virtue of being at standard conditions, I know I'm still talking about 298 Kelvin. I forgot to put that negative sign out there. And then times my natural log of K. So I want y'all to take a minute. I'm going to give you a minute, and I'm actually going to give you 2 minutes. See if you can't rearrange this equation and solve for K. This particular algebra was something that I noticed was tripping students up. Let's make sure that we know how to deal with these natural logs, right? So how do I do the inverse of a natural log? Okay, so everybody take a minute and tell me what this particular equilibrium constant would be here. And I guess I should open that up. You should get a gigantic number, right? Because we got this huge negative number for delta G. So it makes sense to get this gigantic number for your equilibrium constant as well. Right. So remember, just from an algebra standpoint here, if I'm going to rearrange this equation, I'm going to divide both sides by that negative RT because I'm trying to get K by itself. So that crosses it out over here. Let me get rid of this so we're not being too confusing. And so now, importantly, I'm left with that natural log of K on one side and this negative delta G over RT on the other side. And this is something that I noticed students getting tripped up on before. In order to do the inverse of the natural log of K, you don't multiply by E. You have to raise it E to the power of that side, right? So it's like I'm raising E to the power of the natural log of K, which means I need to do the same thing over here. I'm going to raise E to the power of negative delta G over RT. And raising some E to the natural log of anything is how we get rid of that natural log, right? So it's really E to the power of negative delta G over RT, not E times negative delta G over RT. And so if we plug in our particular values here, what we would get is that K is equal to 1.62 times 10 to the 38. Okay, now signs are something that are kind of easy to forget. So what if I had forgotten to put in this negative sign here? Again, one of the things that we really need to understand is this relationship between delta G naught and our value for K, right? Because they're both telling you the same pieces of information. If I got a very small number for K, I would know that something went wrong, right? Because that's not what my delta G is telling me is happening. So delta G less than 0 means that K is going to be greater than 1 because they're one and the same sort of pieces of information. Yes, one of them's your equilibrium constant, one of them's the free energy, but they're intimately related to one another. So if your delta G is telling you your reaction is spontaneously progressing towards your products, your K better be telling you that this reaction favors the products as well, right? And now what we introduced is this variable E naught cell, or this quantity E naught cell, our standard potential. And these are all equally related to one another. And again, we have our condition for spontaneity for our E naught cell, where that value has to be greater than 0, right? So all of these quantities are very closely related to one another. If we have one, we can always work to find the other two. All right, and then lastly, we're going to cover what happens if we have a battery at non-standard conditions. All right, so if we remember, we had said that standard conditions meant that we were talking about, well, first what we learned was our delta G naught. That would be standard conditions, right? Those very stringent set of conditions, 298 K, 1 molar solutions, and 1 ATM for all gases. And that's the same for our E naught of our cell. So that's a battery run under those very specific set of conditions. Well, what if we want to run a battery at non-standard conditions? Well, our analogous quantity for free energy was just that delta G, which didn't have any sort of conditions set to it. And we're going to now define an analogous quantity for our cell potential under non-standard conditions, E cell without the naught. All right, so if we remember, we said that delta G was equal to delta G naught plus RT natural log of Q. And then what we just learned was that delta G naught is equivalent to negative NF E naught cell. So what we're going to do is just plug in an analogous quantity for our delta G, where this is equal to negative NFE cell. Plus, and then we still have our natural log of Q, right? And this is really the bit that is allowing you to input into this equation what your conditions actually are, right? Remember, Q is just the value of the equilibrium expression. Regardless of whether you're at equilibrium or not. Okay, so basically now what we have, just subbing in what we just learned previously, is now this new equation here. All right, what we're going to do is simplify this equation by dividing every term we see here by that negative NF. Right, we can do whatever we want as long as we do it to both sides. Since this is addition, I could have just put one of them in here, but I'm going to have to hit both of those terms, right? And so what we see is this will simplify to the potential of our battery at any conditions is equal to the standard potential of that battery minus RT over NF natural log of Q. And this thing right here is what's called the Nernst equation. All right, allows you to calculate the potential of your battery at any conditions. Right, and again, you can see that, hopefully you can see that it just came directly from this equation here, our thermodynamic equation, that allowed us to calculate the free energy at any conditions. All right. And again, we just took advantage of this relationship that we established between our potential of our battery and that free energy. All right, so now let's say that we have, let's use our Nernst equation here. So actually, for the sake of trying to get in some practice, this is a fairly simple equation to use. We're just going to plug stuff in. I wanted to do a kind of a long example that incorporated all of what we've done for this semester. And so then we'll incorporate, or rather this chapter. And so then we'll incorporate this question into, or this particular equation into our long equation here. But this is what I want you all to sort of work on for the rest of the time, is one of these longer questions that's going to incorporate everything, right? So I'm going to give you an unbalanced redox reaction. You're going to tell me what's being oxidized and reduced. We're going to balance it. We're going to figure out what the standard potential is. And then we can figure out, finally, using that Nernst equation, what the potential is outside of standard conditions, right? If you haven't noticed, I like putting these problems at the end of all of our units just to kind of illustrate to you how what we've learned ties into one another. right? To the extent that you can see kind of like the overarching picture that's being painted in a particular chapter, you're going to be way better off at remembering each little piece of information than kind of viewing it as like this random collection of facts. It's not a random collection of facts, right? So if you can see how everything ties together, your brain will just be much happier in retaining that information. Okay, so we're going to have an unbalanced chemical equation here. All right, and so given this one simple chemical equation here, we learned how to do just a whole bunch, right? So first, determine the oxidation numbers. Say Q. All right, so again, just kind of this big ugly problem that kind of summarizes everything that we've learned how to do in this chapter, or at least a lot of what we've learned how to do in this chapter. So this is just a great practice problem to make sure that you've sort of comprehended what's been discussed thus far. So take a minute to start working on this. It might, just full disclosure, it might run over class time in terms of me going through and answering this, but I'll post this video afterwards. That's kind of my point of wanting to make sure to go over this particular example, is to have it posted as a good practice problem for everybody to review. All right. So what I'm going to do is give you guys a few minutes to start in on this, because I know you're going to need a head start. And then I'm going to go through and start picking away at it here. All right. All right, so to determine oxidation number, a few of these are easier than some of the other species out there. Actually, 3 out of the 4 are really straightforward as long as you've been paying attention to our rules here, right? So that very first rule is that any element in its standard state is going to be 0, meaning like when it's neutral and all by itself. So that would pertain to the tin on my reactant side. So that's going to be 0. All right, and then the other easy rule was that if you have a monatomic ion, a single atom ion, its oxidation number is just the same as its charge. So I can fill in this one here and this one here. All right, so then the hard part is our polyatomic ions, okay? And for that, we got to remember 2 things. one, that oxygen in a polyatomic ion is always just going to be -2. And then the other important bit is that everything has to sum up to be the charge on that ion, right? So I have 2 chromiums and 7 oxygens. If I plug in those oxidation numbers, everything is going to have to sum to -2. All right, so now again, what I need to know one of these 2 components, and the one that we do know is the oxygen. So that's -2. All right, so then I'm going to have to use this to figure out what my chromium is. This is -14. If I add 14 to both sides, it will get rid of it there. Right, so what I have when I rearrange this is that 2 times the oxidation number of chromium is 12, which is why I know that my chromium is +6. Okay, I think maybe if you knew the trick about oxygen, maybe the other place you would get tripped up is make sure to account for the fact that there are 2 chromiums in this formula. All right, so then I'm going to look, for me, I just look at what goes down and what goes up. The thing that goes down is being reduced. The thing that goes up is being oxidized. You can also remember that losing electrons is oxidation and gaining electrons is reduction. Both of those are 2 ways of approaching the same thing, trying to figure out what's being oxidized and what's being reduced. So in this particular reaction, I see that my chromium is being reduced and my tin is being oxidized. Again, just one check that you can have for these particular oxidation tables is you should always see one thing being oxidized and one thing being reduced. If they're pointing the same direction, both numbers go down, something went wrong in there, right? It's always going to be the case that something's oxidized and something else is being reduced. All right, so now we're going to move on to the balancing of these chemical equations. Okay, we got that part covered. And remember, for our balancing, we had this procedure here where we were going to split it into these 2 half reactions. That's really the shtick behind balancing these redox reactions, is you have to use this half reaction method, really because you have to account for the change in the number of electrons that occurs. All right, so this is my procedure that I'm going to be following here. I'm going to split it up into my oxidation reaction and my reduction reaction. My oxidation is that tin being oxidized to the tin 2 ion. And my reduction reaction is my dichromate being oxidized, or being reduced rather, to chromium 3. All right, and one of the things that you can see right off the bat is I'm missing oxygens from this side over here, and that's when we add in our waters and stuff. But the first thing that you're going to do is balance all elements that aren't oxygen or hydrogen first. And so in this case, I need to make sure to balance my chromiums in my reduction reaction. My oxidation reaction, I don't have to touch because they're already balanced, but I do have to balance it with my reduction reaction. Okay, so now I'm going to balance all oxygens and hydrogens. For my oxidation reaction, I don't have to worry about it because I don't have any oxygens or hydrogens there. But for the dichromate, for my reduction half reaction, I am going to have to worry about that. So how do I balance those 7 oxygens? I'm going to add in 7 waters over here. All right, and so that solved my oxygen problem, but now all of a sudden I've introduced this new problem of balancing, of having hydrogens. And so we're going to balance our hydrogens by adding hydrogen ions, H+. Okay, so now everything from both of these half reactions is what's called mass balanced. If I counted tin, I'd have the same number on both sides. Counted chromium, same number on both sides. Hydrogens, oxygens, same number on both sides. So from a mass perspective, all atoms are accounted for. What's not balanced here, and this is the really tricky bit about these oxidation reduction reactions, is you have to balance the charges. So what I'm going to do is make sure that my charges are balanced on either side, and any imbalance I'm going to correct by adding electrons. Over here, there's no charge because it's neutral. Over here, I have a charge of +2. So I'm going to balance that out by adding 2 electrons to my product side. All right, so now if I take my net charge on this side, it's also 0. All right, so that's what we mean by charge balance. Make sure the net charge on both sides is 0. Let me move this down a tiny bit. Okay. All right, if I look over here, I have 14 positively charged protons, -2 for my dichromate charge, so that's +12 over here. And if I look over here, I have 2 of those chromium 3s, so this is +6. So I'm going to have to add 6 more electrons to this side of my reduction reaction. And again, this was just a little, well, just to note, because now when I sum everything up, it'll equal +6. All right, so to zoom out here, this is another check that we sort of had said that you can make, is you should always be adding electrons to the product side of your oxidation reaction and the reactant side of your reduction reaction. All right, and now I'm going to get to sum these up together. The only thing is I'm going to have to sum them up in such a way that my electrons cancel out. So since this reaction produces 2 electrons, but this one consumes 6, I'm going to take this whole thing and multiply it by 3. Right, so then when I sum everything up, it's 3. Oh, no. Try to be good with my states here. Okay, so now I'm just going to cancel what I see on both sides. In this case, the only thing I get to get rid of are those 6 electrons. So my balanced chemical equation for this particular battery would be the following. All right, and this was balanced under acidic conditions, which makes sense because I have protons left over. Remember, if it's under basic conditions, we said you have to introduce one step in the middle here after balancing your hydrogens with H+. You got to get rid of them by adding OH- to both sides in order to cancel out that H+. So that would have been the difference if I had said under basic conditions. This particular reaction occurs at acidic conditions. All right, so now I want to determine the standard potential of my battery. All right, I'm also going to copy down my 2 half reactions here because that's what I'm going to look up on my table. Okay. So importantly, I think the one thing that we need to make sure that we understand is that this E naught cell is equal to the difference between the E naught of my cathode minus the E naught of my anode. Well, how am I supposed to know what's what? Well, remember, oxidation always occurs at the anode and reduction always occurs at the cathode. So those are what my reactions that I'm going to look up, and importantly, the order I'm going to put them in when I do my subtraction here. All right, so going to my page here, get rid of this. And again, we said looking at this table here, remember that the things that are at the cathode are going to be listed towards the top, or at least the reactions that are most favorable at the cathode are going to be listed at the top, and the anode reactions towards the bottom. Okay, so that just kind of gives you a hint as to where you're going to start to look on your page, right? Kind of skim from the top down if I'm looking for my cathode reaction. In this case, I see it here. So let's grab this. This was my cathode reaction. And then my anode, I'm going to kind of scan from the bottom up to try to find that one because those reactions are more favorable at the anode. In this case here is my tin. Oh, and I guess real quick, when we're looking for the oxidation reaction, remember we're actually looking in the reverse direction because the only thing that's listed are reduction reactions. So when we go hunting for our oxidation reaction, we're going to have to look the other way. Oops. All right, so here's the anode. Okay. And one thing that we want to make note about with these calculations, because I feel like this is a very easy mistake to make, is I multiplied this reaction up here by 3, but the stoichiometric coefficients do not appear anywhere in this equation here, right? So when I'm going to use this equation, no stoichiometric coefficients. It turns out that the fact that there was this 3 here to balance that equation doesn't actually impact the potential of this reaction at the anode. What it will do is when we calculate our free energy, we will put in that stoichiometric coefficient. Okay, so it's a little bit weird because when we were calculating delta G's, we very much so looked at those stoichiometric coefficients. That's part of how we calculated it. But notice no such terms appear in this equation here. So you're just going to straight up use the values from the table, regardless of how they were balanced. So I'm going to take that 1.33 and I'm going to subtract that 0.14. Okay. And so here, my standard potential for this particular battery is the 1.47 volts. That's the standard potential for my battery. Oh, whoops, that's not what I wanted to do. Okay, cool. So now we're going to do another thing that we don't want to forget that we learned how to do. It doesn't quite fit into the same quantitative scheme as to what we learned, but we should be able to summarize the contents of this battery in that standard cell notation. Okay, and again, I'm going to grab those two half reactions so we can look at those. All right, so remember, it's kind of like, looks like this format here. Here's your anode material, anode solution, cathode solution, and then the cathode material. All right, so my anode material is going to be that solid tin. And my anode solution is going to contain those tin ions. When I jump over to my cathode solution, both of these, and actually let me be good about my subscripts here, AQ, AQ, AQ. All of these appeared in my solution at my cathode. All right, so I'm going to have to list all of those. You don't have to include the balancing coefficients, but do include all the formulas separated by a comma. Okay, so then what is my anode material? Remember, we talked specifically about these cases where you have in solution both what's being, both the reactants and the product side of your reduction reaction. We saw this example before, where if we have everything here aqueous, then you're going to have to use a platinum cathode. Really, you're going to have to use some inert metal cathode. And we're just going to default to platinum in this course, okay? Because it's great at conducting electricity without being consumed in the reaction at all. All right, so because everything on both sides of my reaction appear in solution, I'm going to use this inert platinum cathode. All right, and then the last one was what is the potential of the battery now that we are outside of standard conditions? So I gave you the concentration of all those ions in solution. All right, so let's put this problem here. Let's get our balanced chemical equations so we can get our K value. Oh, I got to give you, actually, you're missing one important piece of information. Would also need concentration of protons as well. Sorry about that. Where's my balanced chemical equation? This thing here. And then, so our equation here was that the E of the cell equals the E naught of the cell minus RT over NF times the natural log of Q. Okay, and remember we solved for that E cell below. That is, what was it, 1.47 or above, whatever. And importantly, this is joules per coulomb, right? It's in volts. So we're actually in joules. Okay. Which is important because we just want to make sure to note that with regard to our R value. So this is now going to be 8.314 times that 298K. My N is going to come from my balanced chemical equation. Really, we got to look at our half reactions, right? Whoops. What were we able to cross out was those 6 electrons. So that's going to be the value of N is 6 times Faraday's constant, which was 96485 times the natural log of Q. So now the only thing that I need here is that Q value. And remember, we're going to get that by finding our equilibrium expression. All right, so Q is going to be the concentration of the products. Right, remember that these coefficients become exponents. I'm going to leave off water, so I'd be like, oh, concentration of water here, but we leave water out because it's a pure substance. All right, so just our aqueous solutions and our gases will appear in our equilibrium constant. Likewise here, I'm not going to include the concentration of solid tin because it's doesn't really have a concentration, but H plus to the 14 and our C2O7. All right, so in order to find that value of Q, again, Q is really where you're punching into your equation that you're no longer at standard conditions. So this is 0.025 cubed times 0.025 squared over 0.025 to the 14th times that 2.5 molar for our chromium concentration. Okay, so equals. All right, so we get a large value for Q. All right, and so then that's just what we'll plug into our cell potential equation here to figure out what it is under non-standard conditions. And what we get is that our potential for this cell is now decreased to 1.33 volts or joules per coulomb. All right, and so that's how we use that Nernst equation. Again, the big deal is that we can then put in our value for Q, which is any conditions, right? So we just find that expression for our equilibrium constant and plug in all of our values that we would get for our concentration. Those have to be given to you. Again, I left out that one at first. I apologize.